This is fundamental problem 3 from chapter 13. A spring of stiffness 500 newtons per meter, that's K, is mounted against the 10 kilogram block. If the block is subjected to the force of 500 newtons, determine its velocity when s is equal to 0, when s is equal to 0.5 meters. When s is equal to 0, the block is at rest, so the velocity is 0, and the spring is uncompressed, which means, if you remember in the book on page 121, when they introduced the equation for the force of the spring, they said it was equal to K times S, or S, since that is the deformed length minus the undeformed length, you could say the force of the spring is equal to K times L minus L naught. Now, you might want to write the equation this way because the S in the equation for the force of the spring isn't necessarily the same as the S that they give you in this problem. So we have two different S's. So in order to avoid confusion from that, you could just say the force of the spring is equal to K times L minus L naught. L naught is the undeformed length of the spring. So here, if the block is at S is equal to 0, that's the length of the spring. And then if the block moves and sometime later the spring has a shorter length like this, that would be the deformed length of the spring, L. Now, if the block is now here, it moved a distance s to get from here to here, so the difference between where the block was here and where the block currently is, that's how far the block moved. So you could say L naught is equal to S plus L. So if we want L minus L naught, you'd have to bring the L naught over here and bring the S over there, but that means L minus L naught is negative S. Well, that should make sense because if you're compressing the spring, the deformed length of the spring is going to be smaller than the undeformed length of the spring. And the negative sign actually is just going to tell you the direction that the force of the spring is acting in. So in this case, the force of the spring, because it's being compressed, is going to act in that direction. So if you want to figure out the direction for the force of the spring on your own, you could just say the magnitude for the force of the spring is equal to K times the absolute value of L minus L naught. That might be a better way of doing things. You could say K times the absolute value of S, and then in this case, it wouldn't matter that the S in this equation here actually has the opposite sign of the S that they give you, because if you're just looking for the magnitude, then the absolute values would be the same. Okay, so I think you should be able to get started on this problem on your own. You would be looking at the sum of the forces in the x direction and the sum of the forces in the y direction. They give you this 500 Newton force here, but you also have a 3, 4, 5 triangle here. So if this is 500 newtons, then you have 300 newtons acting in the negative y direction and 400 newtons acting in, let's call this the x direction, and this the y direction. So you have a force of 400 newtons acting in the positive x direction. So I would like you to at least get started on this problem on your own and look at the sum of the forces in the x direction, find the acceleration in the x direction, and then try and use kinematics to find the velocity when the position is equal to 0.5. For this problem, they said that the contact surface is smooth, which means we can ignore friction. And if you are ignoring friction, looking at the sum of the forces in the y direction, we would just have the normal force acting upward and the force of gravity acting downwards. So if you did look at the sum of the forces in the y direction, it would just tell you what the normal force is equal to, which isn't going to be important when you look in the x direction if you don't have any friction. So look at the sum of the forces in the x direction, find the acceleration in the x direction as a function of the position, and then see if you can find the velocity when the position is equal to 0.5. And when you're ready, you can unpause the video and see what the solution is. Okay, so if you look in the x direction, you have a 400 Newton force acting in the positive x direction, which is the x component of this 500 Newton force. The force of the spring acts to the left, and that force is 500 times the absolute value of s, but s is going to be positive because we're pushing the block this way and we're starting at 0, so you could just say 500 times s, and because that force is acting to the left, when you sum up the forces in the x direction, you have 400 minus 500s. That's equal to the mass times the acceleration. Divide both sides by 10 to get an expression for the acceleration in the x direction. Then you can use equation 12.3, and you would be using it just for the x component. So you could say this is the x component of the acceleration, this is the x component of the velocity, the x component of the position, the x component of the velocity there. It's only moving in one dimension, so nothing's really happening in the y direction anyways. Then we're going to integrate when s is equal to 0. I know v is equal to 0, so that gives me my lower limits of integration, and I'm going to leave my upper limits as s and v. Then I integrate, I can solve for v squared, and I get an equation for the velocity as a function of s. I can plug in 0.5 for s to get the velocity when s is equal to 0.5. Remember, because this is v squared, when you take the square root, it could either be positive or negative. So we are going to choose the positive solution if we are looking for the velocity when the block first passes through 0.5 meters. But as the position increases, the force of the spring is going to increase also. So eventually you'll reach the point where the force of the spring is going to be larger than 400 newtons, in which case you're going to have your acceleration now pointing in this direction, so the crate would slow down, and then eventually the velocity would become 0, and then it would turn around and start going this way. And so the negative 5.24 meters per second would be when the crate is back at 0.5 meters, but now moving in the other direction. So if you have a crate with a spring attached to it, and let's say you weren't applying this 500 Newton force, so if you just had the crate with a spring and you displace it and then let go, you'd find the crate moves back and forth like this. So when the spring is stretched, the force of the spring would now be acting to the right instead of to the left. So that concludes fundamental problem 3.